How would you classify it? Wrong.
I was just repeating what they said.
What it really is a chronic respiratory failure with a superimposed respiratory alkalosis. Okay. Look at the bicarb. The COPD patient, right? If I take that bicarb and divide it by 0.6, I get a value of 80. So his normal PCO2 is somewhere in the range of 80. But he's hypoxemic, so he hyperventilates down to a value of 57, which is the respiratory alkalosis being superimposed on chronic failure. Yeah.
So, if we have more blood tests, you would want that answer rather than what?
No, classically it is defined as metabolic alkalosis, but you by now should be able to figure out. I would never ask you to classify that on an exam, but I might ask you what intervention would you want to attempt to do. If he's still hypoxemic on that 6 liters, maybe we need to look at using a high flow system as opposed to using a low flow system. Okay. He's also spiking a temp, or he's got a white count that's elevated. He's got extensive pneumonia, so there's other things that we could look at too. But I believe this was one case that somebody brought from clinical one time. Fit in perfectly with this. Okay. Last day for 2250 is on Monday the 20th. We have an exam scheduled for the 21st. Do you want to move that up to either next Tuesday or Thursday?
No. Oh, please. No, not really.
Well,
Hey, think about it, people. Think about it.
I mean, if we have that midterm, midterm too.
When?
On 23rd.
We're having a what?
Would you want to move it till the 16th? Okay, fine. I'm just putting that out there. Well, I can't do both, guys. Yeah.
Why don't you want to move it?
Yes, Patricia. Yeah. Yeah, that's fine. Just recognize that if you haven't completed it, that's your deadline for getting it completed.
So this is the last day, then we have exams, this is the next clinical, then we have the different. You don't want to move it, I don't care.
Well, you guys think about it, and obviously before next Thursday, let me know that you want to move it. But I'm definitely giving you that option. Deadline for the flu vaccination is October 31st. I don't know why I put that in there. November 13th, last day to drop the course, just in case.
Real nice, Rick.
Well, I'm going to be really nice because I'm changing that to December 16th. So you have towards the end of the semester to complete it, okay?
Totally ridiculous.
There's that first day handout you really should take a look at. I'm just saying. Okay? And you're going to let me know what you want to do with the exam too. Okay? All right. And what I'll try to do is post online the answers to that practice test I gave you, just to kind of get a feel. All right, we're going to revisit this concept of buffering and how we manage to control acid-base balance. And I'll end with just a short review of the concept of standard bicarbonate and of base excess and buffer base. But first, how about a video? Oh, wrong mouse. Wrong mouse, sir.
Nothing this winter.
That's just awful. Did you have to explain it to her? Oh, good God in heaven. Can we continue? Newlyweds, you got to explain them everything, you know. Okay, a buffer is again defined as something that that prevents a large change in hydrogen ion concentration. Analogy I use is a sponge. You put it into the environment, it soaks up the hydrogen ions which are present. And we actually call this process a conjugate pair, and we'll talk more about that in a second. We know that acids have an excess in protons. That's why they have a positive charge. And the strong, we can define or differentiate between a strong and a weak acid by the degree to which it dissociates into hydrogen ions from its natural compound state. Examples, hydrochloric acid and sulfuric acid are very strong acids because there's very few in solution hydrochloric molecules. They're primarily hydrogen ions and chloride ions. Weak acids is where incomplete dissociation occurs, and some examples would be carbonic acid or acetic acid. On the top you can see the strong acid with very few instances where I have hydrogen chloride joined together in solution. It's almost all hydrogen ions and chloride ions. Conversely, there's very few instances where I have bicarbonate and hydrogen ions in solution. There almost always has carbonic acid. So the distinction between the strong and the weak. There are many fixed non-volatile acids that we talked about them before through metabolic processes of the breakdown of proteins, carbohydrates, and lipids. And these cannot be excreted as carbonic acid does through the lungs. They have to be excreted as a liquid through the kidney. And as we'll find next time in moduli, oh, it's not that funny. In moduli, you'll end up seeing that's one of the functions of the kidney is to excrete waste products, including these acids which are present. Under normal conditions, as you break down proteins, carbohydrates, and lipids, you do have these acids formed. They're in such small quantities that the kidneys can handle them. It's only in situations where you have an excess being present. Classic example is if you don't have oxygen present, they can't go through the normal oxidative phosphorylation process of the Krebs cycle. You develop lactate and lactic acid as a byproduct. And if there's an extensive amount of that, you end up having a significant metabolic acidemia because the kidneys can't handle it. Okay. We talk about them. We'll just skip through that one and go on to the volatile. Again, is the only thing that is there is carbonic acid. And this acid itself is in equilibrium with the dissolved gaseous component, the arterial PCO2. So we use that as a surrogate. Anytime there's a rise in carbonic acid, there's a rise in PCO2. They go hand in hand. It's linear, and we can use one as a surrogate for the other. If you look at the volume of acid that is excreted, it's tremendous by the lungs, very limited by the kidneys. And when we get to metabolic acidemias, we'll find that there's a lot of things that can be ingested, a lot of poisons that can end up causing an increase in these acids these fixed acids being present. As far as things that are basic in nature, meaning alkaline in nature, they can only be regulated by the kidneys. So if you have an excess in excess ingestion, say for instance of sodium hydroxide, can't think of another base that you might ingest. but it's the kidney that it has to be responsible for management of that. The primary base or the primary alkaline item in the body is bicarbonate, and we know that that is regulated by the kidneys. A couple different buffer systems, and again, they're there to prevent that large pH change. There's some that are in the plasma, some that are in the erythrocyte, and some that are in the urine. These are the primary plasma buffer systems. Really what I want you to know more than anything else is that it's carbonic acid, sodium bicarbonate. Obviously, that's an open buffer system, and I think I got a slide on that to go over it again. The other one that you should be aware of are their proteins within the plasma are very strong buffers, both albumin and other proteins. And this is a slide showing that it's an open buffer system because it can be eliminated through ventilation. So as the CO2 levels rise due to the carbonic acid rising, I can control that and eliminate it through alveolar ventilation. I can't do that with what happens in the blood as far as something buffering those hydrogen ions. They just are held onto them until they're able to be released in another fashion. They can't. There's nothing for them to do to excrete those hydrogen ions as like happens with CO2. So here's what happens when you have a strong acid, say hydrochloric acid. There's lots of hydrogen ions that are free. When it's placed in presence with a buffer system, a buffering agent like sodium bicarbonate, if you remember back to 1060, there's that exchange that exists between ions. It's one type of reaction you have with an exchange reaction. And that's what ends up happening here. The hydrogen ions and the sodium ions change partners, so you end up having carbonic acid formed and sodium chloride. Often what happens in the buffering process is you have, well, not often, it does, you have a strong acid being neutralized to a weak acid and the salt of that acid, and that's basically what you end up seeing here. Hydrochloric acid being changed to being a strong acid, being buffered to a weak acid, carbonic acid, and that salt. Say you had a little bit of a weaker acid, it doesn't have as many hydrogen ions as hydrochloric acid. Again, it doesn't dissociate as much, like lactic acid. Same idea here, bicarbonate could be the buffering agent, and you end up with carbonic acid, a weaker acid than lactic acid, and a salt, sodium lactate. Same thing happens on the base side of the equation. Here, the acid that is being used to neutralize that base is carbonic acid, a acid which has a ability to contribute a hydrogen ion. So what ends up happening is that you end up having sodium bicarbonate formed, as well as, which is basically a much milder base than sodium hydroxide and water. Within the erythrocyte, the thing to remember is that we have a couple different mechanisms to control acid-base, biggest one being hemoglobin, but there's also a potassium phosphate. If you remember, potassium is the primary intracellular cation. It can also act as a replacement for the hydrogen ions in the process, but it's really the hemoglobin that is the key one. Hemoglobin is unique in that it can be both a buffer of acids as well as a buffer of bases. And that characteristic where they can buffer either substance is called amphoteric. So hemoglobin is an ampholyte. I just like that word. You can spring that one on your friends when you're bored. Use that one in Scrabble. That'll really drive them crazy. Amphoteric. In the urine, as we'll find, there's some buffering systems there also, including the carbonic acid bicarbonate buffering system. In fact, that's one of the ways that the kidney creates bicarbonate is by utilizing that system, and we'll talk more about that when we get to the kidney. I'll leave it at that for now. So we know that these buffer systems are going to react within moments of the acid level being increased. When that fails to fully control the acid-base balance, it'll go ahead then and stimulate the respiratory system to increase minute ventilation. That occurs within minutes. And then finally, the kidneys will respond within hours to days. I think we've covered that slide previously in the past. And lastly, I just want to talk and revisit these three indices that exist: standard bicarbonate, and then base excess, but we need to talk about buffer base before we talk about that. This goes way back in time. This was actually one of the first blood gas analyzers, and you didn't have a machine which analyzed each value. I'm sorry, you had to analyze each of the three values separately on three separate analyzers to be able to get a blood gas. Now we shoot it in the machine, and 15 seconds later it spits out some data. We're talking hours to be able to determine a pH, a PCO2, and a PO2. This is from 1954. How do you like that? We know what the bicarbonate is. The plasma the standard bicarbonate is basically taking that bicarbonate level and adjusting it to a normalized PCO2. And what it does, again, is it takes that respiratory influence of a sudden change in CO2 secondary to abrupt cessation of ventilation or an abrupt increase in alveolar ventilation. And basically, we're just able to isolate out what's going on over and above that. And Manley does a really good job of explaining the difference between the bicarbonate, the standard bicarbonate, and actually there's another one, the T-standard bicarbonate, which is the most accurate of all, but is never done in the process. So here's a situation where I have an acute respiratory acidosis, and I have a bicarb that's elevated. And the question is that bicarb truly as high as it seems? Is there that much of a kidney response? In other words, is this a patient who has had a chronic CO2 problem to begin with? What they would end up doing to evaluate this, and now it's all done through calculations, it's not done through an actual measurement, but they could take that blood and using a device called a tonometer, expose that blood to a PCO2 of 40, and eventually the CO2 will diffuse out of the sample and equilibrate with the blood. You then go ahead and remeasure the bicarb level, and that's called the standard bicarbonate. So here we reanalyzed it with our PCO2 of 40 that's been tonometered, and I end up seeing the standard bicarbonate being something significantly different than the measured bicarbonate initially. So we've taken away that hydrolysis effect, telling me that I still do have some metabolic response that was there prior to this acute change. Yeah?
Why would it be 36 in the beginning? Because of the high CO2?
Mm-hmm. The CO2 was probably elevated in this person overall anyways, but that acute respiratory acidosis that ensued for whatever reason now drove that arterial value higher. Some of that through the hydrolysis effect made that bicarb look higher than it actually is. Okay. Here's another example. It appears to be a respiratory acidosis with minimal of technically no, but probably no compensation in the process. After we adjust the PCO2 through tonometry to 40, remeasure that standard bicarbonate, I find out that I have a standard bicarb of 20, truly tells us that we have a mixed acidosis present. So although this one doesn't appear to tell me there's something wrong metabolically, really there is, yeah.
You don't want to do the calculation where every 10 PACO2.
Not yet. That's coming. Buffer base. Okay. The carbonic acid bicarbonate buffering system is only one of the buffering systems within the body. We're going to call all the buffers that are present something buffer base, or BB. Not only including bicarbonate, includes proteins, hemoglobin, phosphates, all those other buffering systems that we just looked at as being in the plasma or in the erythrocyte. When that buffer base level drops, when there's a lot of fixed acids present that they need to be buffered, or when for whatever reason we lose base in some fashion, so either an increase in acids or a decrease in existing bases, a metabolic acidosis would ensue, and the opposite would be true with the metabolic alkalosis. Not that I really care that you know this, but the actual normal value for a normal hemoglobin level is about 48. That does change, though, as the hemoglobin level changes. That's why I don't care that you know that number of 48 milliequivalents per liter. So when we look at this base excess value, it's really just this observed buffer base, what they measure, minus the normal of 48, and the normal value for base excess is somewhere between plus and minus 2 milliequivalents per liter. In the old days, this is how it was calculated. Not a chance in the world that I would ever do this today, or even bother to explain it, but it's looking at this top curve here is buffer base. This line horizontally is bicarbonate. This curve is base excess, and you line them up and blah, 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 blah. Not a chance. So let's say my observed buffer base was 58. My normal buffer base is 8. That means that I must, 48, that I must have a difference between the two of a positive 10. And that means that either you have an excess in base within your body, or you've lost acids in some fashion. There's various substances, when you ingest them, you actually increase the buffer base, and losing acid could be something as simple as vomiting. Here's an example where the buffer base is 40 and the normal was 48. I have a deficit of 8. It really should be called a base deficit, but we just say a negative base excess, which, when you think about it, is really a stupid way to express it. A negative excess. There is also that your book talks about, I'll just mention it, you can forget it. But just like we had the standard bicarbonate being adjusted for acute elevations in CO2, I can do the same thing with the base excess. And it ends up being calling the extracellular fluid base excess. Bleh. So here's one out of your text, in case you've never seen this book before. Yes, Patricia?
So, eventually, on a test, we'll have a problem with the blood gas, and we'll have to calculate the standard bicarb.
No. No, you'll never have to calculate the standard bicarb. I may give you a standard bicarb, but in order to calculate it, you would have to have a machine to literally expose that blood to a PCO2 of 40, which, I mean, how am I going to do that in a test? All right, 25-year-old woman arrives in the emergency department in a coma. These are her blood gas values. What do we think about them? I'm sorry? Good. Base excess and bicarb don't match each other. In theory, if my bicarb goes up, bicarbonate is one of the bases in that buffer base, you would expect to see that value rise. What else? What else is abnormal about the blood gas? I'm sorry? What don't add up? I'm not following you guys. I'm hearing blah, 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 blah. And they are. Okay. I don't tell you what the FiO2 is. So it could have been that they were on a higher FiO2, but let's assume they're a room air blood gas. It's mathematically possible to have that the combination. What do you notice? How would you classify this in the traditional sense? Now I got you guys gun shy, don't I?
Respiratory acidosis.
Okay.
Compensated?
Partially compensated.
Well,
The bicarbazella, I'm just saying classically, how do we do it? Okay. With, what's the cause of the hypoxemia? So it's probably a situation where you have the hypoventilation as your cause. Okay. Now, Steve's right. If I have a PCO2 of 80 in an acute situation, I probably have some hydrolysis effect going on. Okay. And if we do look at that as a 40 torr change from a normal of 40, that means that my bicarbonate would change by 0.32, or I mean my pH would change by 0.32. 7.16 plus 0.32 would be 7.48. It doesn't quite fully account for what's going on, but at least there's some indication that that bicarbonate of 28 probably isn't real. What else could we do for this, or what do you think needs to be done for this patient?
So you're saying the bicarb is really lower than 28?
Yeah. Yeah, definitely. You could get a standard bicarbonate. Okay. What else?
you could put on a ventilator.
Probably need to be intubated and ventilated. Okay. What else? Clinically, what else would you expect them to do in the ER? Intubate, put them on a ventilator, yeah. What do you think the cause of this is?
Could be an overdose.
Could be an overdose. Pretty good chance it's an overdose. So what would you do for that? Yeah, give them some Narcan. If it's an opiate that you're suspecting is the cause of the overdose, in actuality, in most cases, they would just give it the Narcan anyways, because we don't know what they took, and it's not going to hurt necessarily. And try and reverse it. Okay, that was what he Malley said also, and I think we'll stop there. Questions?